This is Bernard Paulson. This is the third lecture in this series. The first one introduced the topic of dynamic simulation, and the second lecture talked about some of the basics of kinetics and multi-scale analysis. This lecture will cover how one implements the simulation procedure. The bullet points, the topics we'll cover in this lecture are as follows. First, we talk about the basic procedure of carrying out a simulation. We will then talk about the graphical representation of the numerical solution that one obtains. I will then talk about an important topic that relates to conceptualizing and understanding the response of your system, and that comes down to post-processing the solution in three different ways, and to think about multi-scale representation of the dynamic response. So first I will describe the basic simulation procedure. So the dynamic simulation process can be broken down into discrete steps. The first one is the formulation of the mass balances to be simulated. They are embodied in this equation that by now should look familiar. For a particular system, we need to define the network and its reactions, which then in turn defines the stoichiometric matrix and the vector x that has all the concentrations in the network we have defined. Then we need to define the reaction rates, the vector v of rate laws. Those fluxes are functions of the concentrations, and they contain the kinetic constants. We normally index the concentrations from 1 to m and the fluxes from 1 to n. So the stoichiometric matrix is an m by n matrix. The next thing we have to do is to specify the numerical values for the kinetic constants. This is difficult. It is hard to get good, reliable numbers for the kinetic constants. These numerical values can be estimated, measured, or inferred, and we will talk about this challenge throughout the class. The kinetic constants are determined once. Then, for a particular simulation, we have to specify the initial conditions. And those are the conditions from which the simulation will begin. So the numerical values for the rate constants are determined once, and the initial conditions may change from simulation to simulation of the equations you have defined. In the introductory lecture, I actually formally broke this down into two different steps. Once you have the equations defined, the numerical values for the rate constants specified, and you've chosen your initial conditions, you can enter all that information into a software package that you then run, and it will generate the numerical solution for you. As we shall see, you almost never look at these numbers, but you try to graphically represent the solution. We talked a little bit about graphical representation in the last lecture, and we will talk more about this important topic in this lecture. The graphical representation is the way we learn how to conceptualize the response of a system and a way for us to develop an understanding of the system and its inherent characteristics. Obtaining the numerical solution is relatively easy in this day and age. There is a number of different equation solvers that you can use. They range from the simple to the complex. They are freeware or commercial software. The two packages most frequently used by engineering students are MATLAB and Mathematica. We will make workbooks available for the problems solved in the text in both formats. I personally like to use Mathematica because it is an environment in which you can develop models. MATLAB is a simulation environment that is well suited for systems analysis, such as the content of this course. Most students at UCSD do seem to favor the use of MATLAB. In this class, we will introduce you to a software package in Mathematica that has been specifically designed to do the sort of dynamic simulations covered in this class. The use of either one of these packages is fine, or any other for that matter, as long as you can get your numerical solution and do the graphical representation. So these clippings shown on this slide illustrate the contents of a simple Mathematica workbook. The green area, and I know you can't read this in detail, and that's not important, shows how you set up the equations. So that's in the green area. The yellow area contains specification of the numerical values of the kinetic constants and the particular initial conditions. Then the area shown in pink are the commands you use to solve the equations. And you notice these are very simple. The blue area is the specification of the graphical results. And once those commands are executed, you get the output shown to the right of this slide. Notice that the blue or purple area that specifies the graphical output is the longest part of the workbook. And you will experience this in this class, namely that the graphical representation is the activity where you end up spending a lot of your time. The numerical solvers inherently give you a solution that is comprised of the numerical value of each of the concentration in your system at a discrete set of time points. And it is a table of numbers as shown in this slide, where you will have time points from T1 onto Tn or even past Tn. Of course, this is just depends on how you specify the number of time points at which you want the solution. And then you get columns for the concentration of all the m x's in the solution at each of these time points. This is inherently what's inside. This is inherently what the numerical solution is comprised of. In packages like MATLAB and Mathematica, you will never see these numbers. These numbers are fitted with a piecewise linear representation or with a cubic spline, depending on the point density in time. And when they are graphed, although they are intrinsically piecewise linear or piecewise parabolic, you will typically only see a smooth curve when you plot the numerical solution. We can post-process the solution, as I will talk about later, by trying to correlate the numerical value of the concentrations at different points in time. So that's a summary of the process of dynamic simulation. It's very simple, comprised of easy to execute steps, and again, in practice, the most difficult part of the procedure for a real situation is to get numerical values for the kinetic constants. Everything else is relatively straightforward. Now, once you have your workbook set up with the equations, the numerical value for the constants, and the particular initial conditions of interest, you get your solution, and then you're faced with the challenge of understanding it. That's when graphical representation of the solution becomes key. There are many, many different ways of representing the solution graphically. In this slide, we show 4 examples. In panel A, we show the baseline, or the most simplest way of representing the solution. Here you simply plot a variable as a function of time, and you get what people typically call the transient response of that variable. In panel B, we show 2 trajectories in one graph. Very often we plot 2 related variables together on a graph. In this particular case, these 2 curves are perfect mirror images of one another. So for every xi that disappears, an xj will appear. How you pick xi and xj is, of course, dependent on your insight into what your system's characteristics are. Panel C shows a multi-timescale response. Here we have a variable that will move upward on a timescale of seconds, then downward on the timescale of minutes, and then upward again on the timescale of hours. So this is a timescale response that might be plotted in 3 different graphs on 3 different governing timescales. Panel D also shows a way of showing a multi-timescale response. This is something we mentioned in the second lecture, where we plot the concentrations on an x-axis, and we make it multiple straight lines, which would correspond to multiple exponential decays. In this case, we see 2 exponential decays. Now, panel C can be concatenated as shown in this slide as yet another example of graphical representation, where you simply take each timescale, give it equal length, physical length on the x-axis, and you just plot the curves right next to one another. So you see already that there are many ways in which you can represent a transient response. An entirely different set of graphical representations are embodied in the dynamic phase portrait. I mentioned this also in lecture 2. This graphical representation shows how one variable, xi, and another, xj, move relative to one another. So you simply plot xi versus xj for all the time points in your solution, and a trajectory, such as the one shown, is traced out. It will have a beginning, time 0, which are your initial conditions. The trajectory will wander around and eventually settle down at another time, at another point in the plane as time goes to infinity. You may already be thinking about, how do I do this for many, many different variables? We will show you how you deal with that later on. There are other variables you can plot in a phase portrait, as we'll talk about later in this lecture, like the fluxes or the pools that we introduced in the last lecture. It turns out that this representation, this graphical representation, is very, very useful once you learn how to use it. This slide shows some of the reasons for why phase portraits are so useful. There are very particular patterns or signatures that show up in the phase portrait that are indicative of certain dynamic characteristics. And by the way, I may often refer to the phase portrait as the phase plane. Those are synonymous. So the phase portrait in panel A shows two variables, x1 and x2, move along a line with a negative slope of unity, or a minus 45-degree line. This means that anywhere on that line, x1 plus x2 is a constant. So if x1 and x2 are conserved, but are moving, they will always move along a line with a slope of minus 45 degrees. If x1 goes down, x2 goes up by exactly the same amount. In panel B, we show another relationship that often forms between two concentrations when plotted against one another. In this case, they move on a line with a positive slope of some numerical value. If x1 and 2 are in quasi-equilibrium, and that quasi-equilibrium is moving, it will move along a line such as that shown in this panel, where the slope will be related to the equilibrium constant k. Panel C shows an L-shaped trajectory. This is indicative of dynamic decoupling between x1 and x2. They move in a dynamically independent manner. Shown here, we start up at the point to the upper left of this plane, where x2 is at a high value and x1 is at a low value. The initial response here is horizontal, which means that x1 is changing while x2 is constant. Once that motion is unfolded, we see a vertical motion towards the end point, and during this vertical motion, x1 is a constant and x2 is changing dynamically. So this is an example of where x1 and x2 move on separate timescales and independent of one another. We will find this feature extraordinarily useful, as we often like to decouple the events that unfold on different timescales. When we do that, we very often have to form pools of compounds through the formation of dynamic aggregate variables. We will see more of this throughout the class. Finally, panel D shows a closed orbit in the phase portrait. This could either be a sustained oscillation over time, where the trajectory just moves around and around on a fixed orbit. This could also be a case where the initial time point and the end time point are the same. Namely, you start at a point in the phase plane, you move away from it, the trajectory swings around and comes back to the starting point. So this is an example of a system that may reject a disturbance represented by what happens initially in the simulation. So you may have changed the concentration or a flux quickly, but the system's dynamic response is such that it returns to the original steady state and is said to reject that initial disturbance. This is often a hallmark of a well-controlled or a well-regulated network. It is robust with respect to perturbations. So there are many different ways of graphically representing a solution. You will learn what fits you best for the particular system that you may be studying. Graphical representation may come with post-processing of the solution that the solver gives you. I'll give you 3 examples of post-processing a solution. The first one involves the fluxes. If we have the concentrations as a function of time, you can simply substitute these values into the rate laws and you can get the changes in any flux in the system as a function of time. Then you can plot the fluxes as the variables of interest. For instance, you can plot how a flux changes with time, or you can form a phase portrait of fluxes, just like you can form a phase portrait of concentrations. The second example of post-processing the solution is to form aggregate variables. As we'll see, the pools are computed from the concentrations by a matrix P that is the pool transformation matrix. We'll talk much more about this matrix throughout the class. But we can take our original concentrations, combine them in different ways to form the pools, and then we can plot the pools. We can plot the pools as a function of time, or we can plot the pools against one another to form a phase portrait of the motion of 2 different pools. That's the concept. Let me give you 2 examples. Example number 1 is the simple reversible reaction, where x1 is converted reversibly to x2. And for the purposes of this example here, I'm going to pick a numerical value of the equilibrium constant of unity. I am showing a pool transformation matrix here that has 1 and 1 in the first row, 1 and -1 in the second row. When I take this 2 by 2 matrix and I multiply the concentration vector, I transform the concentration into pools. And they are shown to the right. The first pool is x1 plus x2, which I get from multiplying the first row in P times the concentration vector. That's an inner product, as you probably already know. Now that pool is the total mass in the system. If this is a closed system, the total mass is always conserved and x1 plus x2 is a constant. The second pool that I've defined is x1 minus x2. And I achieve that by putting a second row into the pool transformation matrix of 1 and -1. Now, why on earth would I want to form this pool? Well, if the equilibrium constant is unity, that means that at equilibrium, x1 is equal to x2. Therefore, at equilibrium, x1 minus x2 is 0. Any deviation from equilibrium will make x1 minus x2 a finite variable, or a finite number, I should say. So therefore, this pool is a measure of the disequilibrium of the reaction, or a measure of a distance away from the equilibrium. So you see in this example, I've taken my two original variables, frequently called the state variables, of x1 and x2, and I transformed them into two different variables that represent different things to me. It represents the total mass in the system and a distance from equilibrium. This is a very, very important conceptual example because we can do the same thing for complex biochemical reaction networks. We can define pools that move on certain timescales, and we can decompose a set of m concentration variables. I shouldn't say decompose. We can combine the concentration variables into different pools that will have physiological meaning for us. The second example of this slide shows this. This is the reaction schema we studied in lecture number 2 that shows the basic trafficking of high energy phosphate bonds amongst the adenosine phosphates. The pooling matrix in this case is going to be a 3x3 matrix because we have 3 concentrations. Let me start with the last row of the pooling matrix. If I put into the last row 1, 1, and 1, I will get the sum of ATP plus ADP plus AMP when I take the inner product of that row and the concentration vector. And that is the third entry in the column vector to the right. And remember, this is related to the capacity of this network to carry high energy phosphate bonds. In the second row in the pooling matrix, I put the entries 2, 1, and 0. And when I multiply that row times the concentration vector, I get 2 ATP plus ADP and no AMP. And remember, that is the occupancy of the adenosine phosphates, of the adenosine phosphate pool with high energy phosphate bonds. So the second and third pool that I formed here represent the physiological characteristics of this network that we discussed last time. The first pool is of little significance as it represents the fastest dynamics in this reaction network. So not all the pools you can form are of primary interest. The third way of post-processing the solution is to do some statistical tests of it. And this comes down to producing correlations or autocorrelations between concentrations. In the first example, I show how the first segment in the response is examined for correlations. In the table down below, you see these purple vertical bars that indicate the range of x's I'm calculating the correlation coefficient for. That is shown in this box. I'm not going to explain what that that covariation formula is, but this is the way you calculate correlations between two variables, something you should know from your statistics class. So I can correlate any two concentrations on any given timescale of interest. I can also do a calculation that calculates the correlation over the entire range, as shown with the blue bars. This is not often as useful as example 1 because variables tend to correlate differently on different timescales in a multiscale system. Finally, example number 3 shows an offset in time. If I suspect that there is a time delay, say, between variable 1 and 2 of 2 time units, I can correlate x2 at time t1 to variable x1 at t3 and so forth. So I can actually take these two columns of numbers for x1 and x2, offset it by any time increment of interest to me, and calculate that correlation. So that would be a way to get at any time delay effects in a system of interest to us. So here you have three different ways of post-processing the solution once you have the concentrations as a function of time. You can calculate fluxes, you can calculate pools, you can calculate these correlations. And then you can do graphical representation of these quantities as well as the primary concentration variables. This all may look complicated, but for a particular system that you will study, you will find that one of these representations suits your purposes. The next topic that I'd like to discuss is the graphical representation of a multi-timescale response. As I mentioned earlier, every phase portrait will simply show the relationship between two concentrations or two variables, but I have many of them. So how do I deal with that? Well, it turns out that you can prepare an array of phase portraits, and it is comprised of a phase portrait between any two variables, and then you tile them together as shown in this slide. First, the diagonal in such a tiled array is irrelevant because I'm simply correlating xi to xi. That doesn't give me any useful information. The second thing I note about an array like that is that it's symmetric. The plot of x2 versus x1 is the same as plot of x1 versus x2, just flipped around the 45-degree line. So an array of tiled phase portraits like this only has to be filled either below or above the diagonal. So that actually gives us an interesting opportunity to represent different attributes of a phase portrait below and above the diagonal in this tiled array. The two spots I just filled in with the animation show an example where x1 and x3 are positively correlated. Below the diagonal, I show the graphical representation of that slope with a positive line, and above the diagonal, I'm actually showing some of the statistical properties. In this case, I give the slope and the correlation coefficient, which in this case is effectively unity. So this graphical representation turns out to be very useful in visualizing multi-scale responses. Let me give you an example. So here is an example of this sort of an array where I have just filled in half of it. The diagonal blocks are just blacked out. And on a particular time scale, 0 to 3 seconds in this case, I can plot the three phase portraits. And for instance, x1 versus x2 is a line with a negative slope of -1. I can then look at a slower response of this system over a few hundred seconds, and I can redo this tiled array, and now I see completely different relationships between the variables in the phase portrait. These are all characteristic signatures that I discussed earlier. So this is the concept of graphically representing a multi-scale response. Let me give you a specific example that will hopefully help gel these ideas in your mind. I'm going to look at a simple series of reactions here. This is a simple pathway where x1 goes to x2, x2 goes to x3, and x3 goes reversibly to x4. And as indicated above the reactions, they will have different characteristic timescales. The first one is fast, the second one is intermediate, and the last one is slow. So this means that the rate constants in the first reaction are large numbers. In the intermediate reaction, they are smaller, and in the slow reaction, they are smaller yet. The dynamic mass balances for this simple system are shown below. So for x1, I see that the forward reaction of V1 degrades it, so I have minus V1, and the reverse reaction of V minus 1 forms it, so I have plus V1. So that's the dynamic mass balance on x1. The dynamic mass balance on x2 has 4 fluxes in it, and on x3 it has 3 fluxes in it, and on x4 it has only 1 flux in it. Those are the dynamic mass balances. What I showed to the right is the substitution of mass action rate loss for these fluxes. So V1 is simply K1 times X1, just the first order reaction involving X1. V minus 1 will be K minus 1 times X2, since X2 is the concentration that drives that reaction, and so forth. You can easily fill in the rest of these equations. To simulate, I now need to specify the numerical values of the rate constants and the initial conditions. I'm going to give K1 and K minus 1 a high value, K2 and minus K2 a lower value, and K3 the lowest numerical value, or the smallest numerical value. Shown furthest to the right are the initial conditions, which we have to specify. What I want to do now is to show you the results of simulating this system when only x1 is present in the beginning. There is no x2, no x3, no x4. And x1 will be converted all the way to x4, and everything will end up as x4 because the last reaction, V3, is irreversible. I can put this a set of equations into Mathematica and into MATLAB and do the simulation. And the workbooks for that simulation should be on the class's website. I get a multi-timescale response, and I've chosen to show it in the concatenated form that I introduced earlier. So you see in the beginning, at time 0, I have x, the initial condition for x1 being unity. The initial condition for the other x's are zeros. Over the first time scale, that is characterized by k1, I see a decay of x1, an increase of x2, and no motion of x3 and x4. So what is happening here is the first reaction, that is fast, is responding. During this time period, x1 plus x2 is roughly a constant equal to 1, the initial condition, because reaction number 2 has not become active yet. So I've chosen the equilibrium constant for this reaction to be 1, so the ratio of x1 to x2 heads towards unity at the end of this time scale. And that would be a 50-50 split, which I'll show as 3/6 on the y-axis here, which of course is a half. When the simulation gets into the intermediate time scale, x1 and x2 have basically become fixed in a quasi-equilibrium relationship with one another, and the dynamics of the first reaction have effectively relaxed and are no longer active. The dynamics of the middle reaction are now active. And during this motion, the total amount of x1, 2, and 3 is approximately unity because no x4 has yet been formed. What is happening on this time scale is the equilibration between x3 and the pool of x1 plus x2 as governed by the second reaction. I have also calibrated this equilibrium constant to be 1, and therefore I get the behavior at the end of the intermediate timescale that is indicated. On the longest timescale or the slowest timescale, reaction 3 becomes active, but the other two are not. They have effectively equilibrated to form a pool of x1 plus x2 plus x3, and that pool is now being converted to x4. I apologize for the fact that this slide shows that being reversible in blue there. It is actually supposed to be irreversible. And during this time scale, the pool of x1 plus x2 plus x3 goes to 0 and is completely converted to x4, which heads to unity, which was the initial concentration of x1. And at that point, the reaction is complete. Note that during the slow time scale, x1, 2, and 3 all move the same way. You may have to listen to me go through this again to conceptualize the response, but it is very simple. It is simply a series of 3 reactions, each one moving on a separate time scale, and the reactions occur in series. I can take that dynamic response and plot it in the form of these tiled phase portraits, and I get a full response that is shown in panel A. It's complicated, and it's better to show this as 3 different sets of tiled phase portraits, each for one of the governing timescales. So first, in red, we look at the fast time scale. In this case, x1 and x2 are moving on a minus 45-degree line, which corresponds to the formation of that quasi-equilibrium, and we get a perfect correlation for that motion. x3 actually goes up by a tiny amount during the fast time scale. And the way this here is prepared, this plot is prepared, I've amplified that magnitude. But if I scaled x3 from 0 to 1, these would just be flat horizontal lines, showing that x2 and x1 are moving and x3 is effectively not changing at all. On the intermediate time scale, I now see a different set of relationships between the variables. Now the phase portrait of x1 and x2 has a positive slope of 1 because now they are moving in tandem after they have equilibrated. The phase portraits for x1 versus x3 and x2 versus x3 now have a negative slope because the summation of x1 plus x2 is being drained and x3 is being formed, as we had described earlier. Then finally, on the slowest time scale, you see all the phase portraits look the same because all these variables are now moving in tandem and the same way. And they're all decaying along a straight line into the origin because they all eventually go to 0. So this is an example of how we can take a multi-timescale response and look at a tiled set of phase portraits for each timescale to help us understand and interpret the dynamic response. In this case, it's easy to conceptualize, and we already could understand the response from the earlier slide. However, for more complicated systems, that is considerably more difficult, and this graphical representation helps you to conceptualize the response. The next step in understanding the dynamic response is to try to untangle the events that take place on different timescales. And this is done by forming the pools and transforming the concentration variables into aggregate variables. In this particular case, I have formed a pooling matrix that is shown in this slide. The first row in the pooling matrix is 1 and minus 1 and 0. And when I multiply that row times the concentration vector, I get x1 minus x2. This is the disequilibrium variable that I mentioned to you earlier. The middle row has half and a half and a minus 1 in it. When I multiply that times the concentration vector, I get x1 plus x2 divided by 2 minus x3. This will represent a quasi-equilibrium relationship for the second reaction after the first reaction has relaxed. The last pool I'm defining is x1 plus x2 plus x3 because that is the final dynamic pool that forms before the whole system decays to 0. So this pooling matrix defines 2 disequilibrium variables and 1 conservation variable. I know that P1 will relax on the fastest time scale, P2 will relax on the intermediate time scale, and P3 will relax on the slowest time scale. Now, if I take the solutions to the concentrations and transform them into the pooled variables and do the tiled phase portrait representation, I get what's shown in this slide. I get only L-shaped traces in these phase portraits. This means that the pools are completely dynamically decoupled, but I already knew that. And you can see, for instance, in the first phase portrait, P1 versus P2, we start in the upper right-hand corner of that phase portrait. We shoot across it horizontally because P1 is moving and P2 is a constant. And then after that time scale has relaxed, P2 moves down to 0. And P1 will already be at 0. And you see a similar interpretation when you look at P1 versus P3 or P2 versus P3. Ideally, this is what we would like to see because we have completely decomposed the system into separate events on different timescales, and I have a full understanding of the events that unfold on the different timescales. So I have been able to decompose the system in time, and I've been able to decompose it in terms of the events that happen on each timescale. This is not always this easy to do, and you're often stuck with having some correlation between pooled variables. It may be only good phase portraits at the slowest timescales or the timescales of particular interest to you. So that ends the lecture, and let me summarize the main points that I've made. First, the dynamic responses of networks are described by the mass balance equations that we've been talking about and shown in this bullet point. There are a series of assumptions that underlie the formation, as we have discussed on several occasions. To simulate the response of these equations, we need to get the numerical values of the kinetic constants, which is difficult, and specify initial conditions, and very often we also have to specify boundary fluxes for open systems, what flows in and what flows out. You will see examples of this in the following lectures. The equations with given initial conditions can easily be integrated numerically using a variety of available software packages. We will, in this class, emphasize the use of MATLAB and Mathematica. If you have not used either one of those prior to taking the class, be prepared to spend quite a bit of time learning how to do so. Doing programming and simulation is a skill that takes some time to develop. And I should note right away that this is a skill set that you will be able to put on your CV once you graduate. You will have the ability to set up complicated network equations, simulate them, and interpret the response. This is an important engineering skill set. And it does take time and commitment to develop. The solution you get, the numerical solution you get, is in a file that contains the numerical values of the concentrations at discrete time points. Normally, you never look at these numerical values, but you look at an interpolation function that Mathematica or MATLAB give back to you, and you graphically display them. Typically, initially, as a concentration changes over time, or in an initial phase portrait. Once you start studying the response of your system, you very often post-process the solution to look at fluxes or pools as indicated, and you will learn how to plot any one of these variables in a meaningful way to call out specific dynamic features of the network that you're studying. We will now go through we will now go through 4 different sets of lectures utilizing what we have learned so far. The first set involves embarrassingly simple chemical kinetics, but these are toy models that will be instructive for you. The second set of lectures will start to introduce generic biological features that one will deal with. The third set of lectures shows you how to build simulators of important biological processes such as glycolysis and the pentose pathway. The fourth set of lectures will show you how to incorporate small molecule protein interactions into simulators. Most small molecules bind to protein and alter their actions. And we will have 2 examples of that in the last set of lectures. When all of this is put together, you are actually in a position, once the class is done, to build realistic simulators of realistic biological phenomena. And as I mentioned on the last slide or so, this is an important skill set for engineers to possess. This ends the lecture. Thank you for your attention.